Okay. Okay, let's start. Let's see. Any questions so far? Anything? No? Good. So we started our discussion. Sure. This one, this much. Let's see. Right. So we started discussion about the vector field, and we will continue today. Hopefully, we will get to massless case, engaging there for that, and probably we will hopefully finish basics of massless case this week, and then hopefully start QED soon. All right, so let's get started. So last time we sort of constructed by starting from a most general Lorentz invariant expression that a consistent Lagrangian for mass C case, so-called Tropa theory, and this section. Oh, by the way, sorry. So we haven't quite fixed last time yet. What is the overall relative sign? So it could be in principle. It could be in principle, for instance, something like plus minus here, and then minus relative minus sign. The sign was fixed. Okay, the relative sign was fixed, and then we fixed that by imposing unitarity, and then we looked at the equations of motion. We asked a consistent, dispersion relations. Okay, and this theory describes theory of disputes, right? So in other words, we saw last time that this can be decomposed into scalar part and then transverse part. What we saw was that this theory only describes disputes, transverse part, but without including this scalar part. Okay, so we talked about that. So today we will talk about the canonical quantization of this theory. Let's talk about canonical quantization of this theory. So to this end, obviously, starting from the Lagrangian, we have to pass on to the Hamiltonian, and then impose, canonical commutation relations, then quantize the theory to get the quantum field, and so on and so forth. Right? That's the usual story that we've been doing so far. So to do that, let's actually look at a. Eventually, we have to therefore derive Hamiltonian density, and then we have to impose equal time commutation relations, and so on and so forth. That's what we want to do. So to do that, the first step is obviously to derive a conjugate momentum, starting from this. So we can rewrite this thing as. So let's continue here. Plus minus 1 half. Then we have 0i, 0i half, because there are two pieces I can combine, and then there is 1/4 ij j, and there is m squared 0, 0 I. Good. So let's derive. So we want to get the conjugate momentum. Yeah, the momentum. So naively, well, by now you know, naively, you might say, oh, okay, this is the vector field. So that means that I have A0 and AI. So now if you look at this action, right? So this is the only piece that has a time dependency, right? So this is the only piece that has time derivative here. The rest is either spatial derivative or polynomials in fields. Okay. So for instance, suppose I want to write it as pi I, which is my conjugate momenta for this piece. So if I write it as like that, Okay. Now remember our notation for this f mu nu was derivative of a mu and anti-symmetrizing it. So in particular, you see that f0i that has time derivative acting on ai, which was what I wanted to see here, and then that's this. But also, you immediately see that f of 0 component is 0, which means that effectively this Lagrangian does not have time derivative a0 acting on it, right? So there's no such term. Okay, so if you do it, therefore, you get, because of this plus minus sign, you get 0. Okay, because this thing is packaged into this f0i, so you have two terms to cancel out the half, and then one of that, because it's linear in this term, you get prefactor 1 if you do it. But more crucially, you get 0. Okay. There are some names under this phenomena, constant of motion, and so on and so forth. But the point here is that, naively we are in trouble, right? Because it's not like for all 4 components we have conjugate momenta, and then if we had that, we can pass it to Hamiltonian. But naively we have an issue. Okay? Why? So hopefully you see what I'm saying. For any q, right? And then if Lagrangian has a q dot, then you want to get P, which is a function of Q and Q dot. So basically, this is the inverting relation between Q dot and so basically this is the Lagrangian transformation that inverting Q dot to the PS order, right? And vice versa. So and therefore you wanted to go from the Lagrangian to the Hamiltonian. But here the point here is that the conjugate momenta for AI exists. That's factor number 1. Factor number 2, it actually has a I dot dependency in it, so you can invert this relation. Here, it doesn't seem to be the case. So let's quickly answer this trouble or this question, and then we're going to write down the basically answer for harmonic quantization. So here, the key concept, as Coleman discussed, is the initial value data. So I'm going to abbreviate it as IVD. Okay. So what is the concept? So we are studying the dynamical system. So here's the time evolution. So this is time trajectory. And then equations of motion basically controls. So the equations of motion controls the evolution of the dynamical system, right? And then for any given time slice, suppose here's my time slice at fixed time 0. And if the equations of motion is a second order differential equation, we know that we have to impose complete set of initial value data so that this particular question of time evolution is well posed. Okay, so there's a dynamical equation, or mathematically you just have to solve a differential equation of some order and some number of variables. And you know that you have to provide at least enough set of initial value data, okay, which are not mutually conflicting. So then this system can be solved. You can understand the time evolution of the system. Okay, so here you have to specify a complete set of initial value data. The point here is that for this Proca theory, the claim is that. So okay, before I write down claim, let's remind ourselves. So equations of motion look like Proca theory. Equations of motion look like, roughly speaking, box plus m squared and mu equal to 0. So each of those 4 components seems to satisfy a Klein-Gordon equation. We derived that. So if you recall, we start deriving. We have this mu nu equal to minus m squared a nu, and then you can impose transversality condition to convert this back into this one. Okay, so we have done that. So naively, we have a second order differential equations. This is second order differential equation for each. This is Klein-Gordon equation for each A mu. This is like 1, 2, 3, 4. So naively, because this looks like 4 separate second order differential equation, naively, the complete set of initial value data seems to be AI as initial value, and then its time derivative, so which in this case I can say Fi, here let me say T0, T0, and then this, and then the time derivative of T0. First T0, not T0. So now it seems like you have to supply this much of information to be able to, form a complete set of evolution equation and system. Okay. So in case you're lost a little bit here, what I mean by that was that for scalar field, we have this equation, right? This is a scalar Klein-Gordon equation, and this is second order. This is two derivative in it. So this is second order differential equation, and then initial value. What do? You provide x, phi at initial point, and then first derivative of velocity at the first point, right? That's why you provide to solve it. What I'm saying here is that since this looks like a set of uncorrelated force field, naively you might say you have to provide all of that, okay? But the claim here is that you don't have to, because otherwise you're in trouble, because here you actually don't have conjugate momentum. Looks like there's a trouble here. The claim is that the complete set of initial value data is just AI, and then this, or equivalently, if you wish, that's that. And in fact, you don't have to provide this too. Okay, so let's quickly see why that's the case. In fact, that's not very hard to see. So first, remember this theory describes a field that satisfies transversality condition, which let me write quickly. This, right? So a field already satisfies this condition. What does that mean? So that means that A0 time derivative acting on the A0 component is the same as this at all time. Okay, so this was one of the equations of motion, meaning field along the on-shell trajectory satisfies this condition all the time. In other words, you don't accidentally excite extra degree of freedom, right? Just because you're going through the time evolution. Is that clear? This is about projecting a certain degree of freedom. So it has to be satisfied all time. So this equation then tells me immediately that this particular equation at any time, in particular at t equal to 0, is related to just AI value at that point. And if you specify that value at that point, you can obviously take the special derivative, no problem. Okay? So this is redundant information, because that's answer number 1. Answer number 2. So the other equation of motion on top of that was this. Okay, from the Professor Chen. So let's look at a here. Sorry. Let's look at a 0 component here. So let's take mu equal to 0 point, mu equal to 0 for this equation. Since 0 component is 0, I get this on the left hand side, and the right hand side is 0 here. So here too. So if you know that this particular equation of motion does satisfy along the anytime trajectory for on-shell configuration, that means that the value of this guy at any point, including initial value slice or surface, also here, this can be phrased in terms of, again, special derivative of f in this case. Okay, so once again, once you specify this, you already have this data in it, so you don't have to put separately. Okay, good. So that answers this question. That no, you don't have to specify everything, but specifying AI as independent degree of freedom, and then associated momenta f0i, or if you like, velocity of that guy, suffices to establish complete set of initial value problem. Okay, so that's good. So that's not. So this is not necessarily a big trouble. So then we can actually proceed and then quantize. Are there any questions? Is that clear what I'm saying? Okay.
Yeah. Is that related that the F0I is the conjugate momentum to AI?
Is it related? So F0I is the conjugate momentum to AI, yes. And then when you say is it related, which part is related to that part?
So that, I mean, you only have to specify two information, right?
Yeah, so this is consistent with basically the fact that the proper theory describes time evolution of 3-degree freedom. So 3-degree freedom and its momentum or its time derivative.
Yes, and then you mentioned from the classical mechanics that if you want to specify the equation of motion, then you only have to specify the position and its momentum, right?
Yeah, of independent position and associated the momentum. Okay, and we don't even just using a description that has a little bit of, if you like, extra information that we need. Yes.
그러니까 A 제로에 대한 인식 컨디션이 필요 없는 이유는 EOM에서 구할 수 있다라는 건데 인식 컨디션이 EOM을 만족해야 되는 이유가 있나요?
Okay, so the question is the information about A0 is already contained in the equation of motion, right? So you know that this equation is true everywhere at any time.
그러니까 외부 이볼루션이 되면은 그 이퀘이션 오브 모션 따르는 게 맞다고 생각하는데 처음 시작할 때 외부에서 퍼터베이션을 줬을 때 그때도 이제 이퀘이션 오브 모션을 줘야 된다. 델타 폴만 친구가 크레이션 빵 주는데
Yes.
그때도 이퀘이션 오브 모션을 충분히 따르고 있는 거야.
Yeah. Okay, so I think your comment is naively, when we study differential equations, right? There is a time evolution, and then we have to separate data, right? And then we can let it go. But why are we here doing something like we are actually using equations of motion, which actually is something that describes how things evolve rather than what is the value at the point. So your question is, well, it seems like we're mixing up stuff. Is that your concern?
Yeah.
Good. This is a first order equation. So this is not quite, if you wish, evolution equation. This is constraint equation. But this constraint has to be satisfied every point. So you don't have a question about this one. Okay? So you might say, what about here? Again, this is a first order in time, if you look at it. So this is not quite second order time equation. Okay? So when we look at this piece, instead of I there, all of a sudden this equation is a first order in time. So in that sense, if you wish, this is not quite just time evolution part of the equation. Okay, this is like diffusion equation if you wish. But nevertheless, so where is it? So if you look at here, for instance, if you look at the I component here, this has a generally two derivative in time, right? And then special derivative, if you wish. This is generally second order in time derivative. Now, that one and this one is actually first order in time derivative. So if you wish, this is a slightly on different status as not, genuine time evolution equation, if you want. Okay, Klein-Gordon equation, eventually if you collapse down to the Klein-Gordon equation, has a two time derivative separately and then special derivative. Right? And this is first order. So overall, A, if you wish, this and that, two equations, especially when I focus on B equal to 0 part, takes a slightly different status. B, since they have to satisfy everywhere, in particular, they sort of act as if it is a constraint equation. Constraint equation because it's literally relating how, this value in terms of other values, right? So this is not actually just saying that, this evolves separately along the trajectory. The reason why we're getting this sort of feature is once again, we wanted to describe a theory of this guy, right? However, we started out with this because we decided to use A mu. That means that, this has a 4, this has a 3, we have to impose extra conditions. So not all of them are independent. I'm just repeating the thing that we already know. So in a sense, we should not take this equation, especially this equation, as a base value. We know that not all of the four-degree freedom are independent. Indeed, this was exactly one of those conditions. Say that, be careful, not all of the 4 is independent. In fact, no. And this is another version of the basically the constraint equation, but written in terms of this formula, especially when I look at the zeroth components. So if you think about it more carefully, basically that's what's happening here to tell you that, eventually this is the answer. But this will get slightly more complicated if we start going into the Mason's case. But anyway, think about it. If you still have a question, bring it up again. Yes.
같은 질문을 반복하는 것 같긴 한데, 그러니까 클래시컬 메카닉스에서 생각하는 X랑 P의 이니셜 컨디션만 주어지면 그 이유를 예측할 수 있다, 있잖아요.
If you assume that your X and P are independent coordinates, yes.
근데 여기서는 지금 X가 AI인 거고, 그리고 P가 FI0인 건데, 근데 왜 그거에 미분까지도 이니셜 컨디션으로 정해줘야 하는지를 모르겠어서요.
Okay, let me just, so in classical mechanics system, yes, as you said, once we given an evolution equation, once we specify this, we are done. So it goes and we can determine this value as a function of t. That's the answer. Here too, if I forget about this subtlety, right, having an extra degree of freedom, if I know that this system describes a 3-degree of freedom, which I label as AI, if you like, then here, by this equation, I just mean that I'm specifying AI, and then basically time derivative of AI. But I just rewrote in terms of M0I, it's equivalent. Does that answer your question, or you still have a question? This is the same, as you said. I'm specifying X and X dot. This is X, X dot.
근데 이제 이니셜 컨디션을 주는 거는 A0를 줘야 되는 거잖아요. 파셜 I FI0의 T equal 0에서의 값을 알아야 된다라는 얘기는 그 두 번째.
Sorry, initial value means that if I know which one is actually physical degree of freedom, I'm giving you value of this cell and its time derivative at time equal to 0. This part of the discussion is to show that, I don't have to specify or supply separately initial values for A0 and its time derivative, because this is already captured by initial data given in terms of AI and its time derivative. That was our argument.
끝나고 나서 여쭤보겠습니다.
Okay. Okay. Good. So with this, we can pass on. Yes.
I think another point is that for the 4 component 0, 1, 2, 3, but we don't need information about 0, am I right? Because we can extract from the information of the 1, 2, 3 from the
Basically, yes. Basically, this composes a complete set of degree of freedom. So So this data is already included once I specify this, because I know they are not separate degree. Yes, that's the same. Yes.
My question is why time is it? Because the
this situation means that since we have our assignment of initial value means that at initial time, we all know the value of our space. Okay.
Yeah.
So the left-hand side of the education is can be calculated by, since we all know the value of space-time, so we can calculate the spatial derivative.
Yes.
So then why space is important than time, more important than time.
Oh, good. So here, good. So the question is why we say that why, if I receive it correctly, why a spatial derivative is not taken as a extra information than specifying time derivative. The good. So that's the question. The reason is, once again, we are taking specific slice, and then that is according to the time evolution. And then if I have this time slice, which is all about the space, specifying a complete set of initial value data is that you have to tell me everything about this slice. Okay, but if I give you everything about this, every value of AI here, obviously, if somebody had your function AI on this, time slice, you can certainly just compute the, spatial derivative along this surface. So once you have this, we can compute this because I'm gonna hand you the function of a space here too, because I'm gonna specify this at the initial time slice. Again, you can take a spatial derivative.
Then my question is why we need to choose space a time slice, because if I interested in some, if I choose that instead of equal time then such as equal space, then I can.
Oh yeah, so that's obviously because we whatever direction I want to solve the equation for, I called it a time. So you can pick any other direction if you want. So in other words, we are doing specifically, Minkowski space quantum field theory. But suppose we pass on to the Euclidean space quantum field theory, where now the metric has a plus, 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 plus. So everything is plus. I can't tell which one is time anymore, right? Everything looks the same. In this case, you can pick arbitrary direction, z. I demand that this direction is special to me. And then I'm going to solve my equation along that direction. Okay? Which means that you have to take a perpendicular slice. You have to specify, once again, you have to provide now complete boundary value data. Here we call it initial value data because we just take this to be specifically in a special time direction, and then I have to specify data on the perpendicular surface. Okay, but if you have the Euclidean, you can pick any other direction and try to solve the equation with respect to that direction, and then once again you have to specify data from the hypersurface perpendicular to that. Okay, so since here we are doing here Lorentzian or Minkowski space, that's why we take time takes the spatial states. Okay, good. So now let's quantize. I'm going to write a lot of answers without necessarily doing computation, and then I will leave the actual computation for homework. So now Hamiltonian, obviously, that Hamiltonian density is this minus Lagrangian. Okay, so clearly. Now you can do this computation. Trust yourself. Since you have everything, you should be able to compute this. And remember now here, this was the plus minus f0I, the Lagrangian is over plus minus I. So if you plug in, you get the following answer: so plus minus. Make sure this is okay. And then if you get this. So now this is just explicit computation. Now, if you look at this, let's write everything in a sense of by lowering indices together. So when you lower this index together to make it square, lowering time comes with the plus sign, lowering spatial part comes with the minus sign, right? Because we are using metric, which is plus, minus, minus, minus. So you see that this overall thing, because if you lower to make it square, it's less or equal to 0. Okay? Now, here you have the lower two spatial, but then it comes with overall a plus sign. There's a minus sign in front, so this also less or equal to 0. Now you just need to lower the one temporal component, which is plus, but there's a minus sign. This everything is less equal to 0. Now you have to lower one of the spatial indices, which comes with a minus sign. Again, everything is less or equal to 0. You see that everything is nicely less or equal to 0, so you know that you have to pick a minus sign to make Hamiltonian bounded to front one. Okay, good. So if you pick minus sign there, obviously now Lagrangian, as you carefully, so minus sign here, minus 1 first f mu nu, and then if you combine plus f m squared a mu. So okay. So now we pick the minus of sign, overall sign of the Lagrangian, then we are ready to quantize here. So now we just need to impose equal time commutative relations, which is schematically QP is delta, QQ EP is 0. So that's what you want to impose.
이게 잠깐 헷갈리는데 그 라그랑겐에서 레스텀에 해당하는 거 둘 다 마이너스 본데 그래서 마이너스 플러스입니다.
Okay, so your question is why this will happen as you pass from Lagrange to the Hamiltonian?
Yeah.
Okay, because if you do it, I'm sorry, I confused. The original formula is this, all right? But then when you try to rewrite in terms of f0, you have to come, you have to add extra term that they give you if you use equations of motion, extra terms. So check this computation. So now equal time commutative relation, obviously now I'm gonna quantize. Here I'm treating obviously AI, then f0i as my two, q and the p. So I'm just imposing that. So it's clear. If I have this, and then, well, I don't know, j, y, p is 0, right? So that's clear. And then ai, ij, I want to impose that as, first of all, ij, exactly, ij, and then ij. So since this is what? This is now minus, because we decided to pick minus sign here to make Hamiltonian bounded from below. And now this is f0i. Then we impose 0i, then we suppress x, and so on. Okay, so you expect this. So indeed, it works out consistently. So now, since you quantize it, you know that you can write your field a mu of x as a quantum field that has degree according to certain normalization of creation annihilation operator that I will specify now. What is that? So there is a profile which we call the polarization vector, which has 3 degree freedom for this guy, which is a function of momentum. And then there's an annihilation operator for that mode, which is for positive frequency mode. So you'd expect that, right? For scalar, we just had that. For fermion, we had the U function, right? That was the positive frequency profile function. Here it is this polarization vector. And then there is our star. And then there's a creation operator
creation operator for that mode, and then negative frequency part, and then only fill in post. Okay, so this quantum field now, vector field, can either annihilate each of these three polarization modes or can create each of those polarization modes. And I just see that this is manifestly real because the profile function appearing, both annihilation equation are basically conjugate of this. Okay, so this manifestly real. So here, what are the commutation relations acting on this creation and annihilation operators? Well, as you expect. If you look at the creation, one annihilation, one creation, and the consistent commutation relation is going to be that. What do I mean by consistent commutation relations? Basically, if you impose this, then if you compute this, you get the right answer. That's what I mean. Okay? So this should be translated into a condition on A and A dash. And when we studied scalar field theory last semester, basically we actually worked out that way. So starting out with this, we just wrote down that, and then we derived the equation like this, such that this is satisfied. We can check backward this time. Okay? And then I'll leave that as a size, because it's a straightforward calculation. Okay. Now, as a comment, just like for scalar field and also for Fermion field, you can also use slightly different normalization for creation and annihilation operators. Basically, you can define an alpha creation or annihilation operator for R mode, which has 2 pi to the 3 half, that's square root of 2e a e r. So in this normalization, as we worked out, first of all, remember this delta function itself is not a Lorentz invariant delta function, right? But if you renormalize this way, then first of all you get QE delta E minus Q. So that is happy combination as you want to see. And then on the quantum field now we have this 2 pi to the cube and then 1 over 3. So there's that rewriting. If you wish, you can do it. You don't like that factors. Okay, so quantization done. I mean, there is a calculation that you want to do it, and you will do it. So now what you can do is that, I just erased nicely. So, see? So I wrote down this long Hamiltonian, which I'm not going to do it. So there's a Fi0 square, Fij square, there's a 2 mass terms. Now, since you have this expression, you can plug in the Hamiltonian expression, and you should be able to show that for the Hamiltonian, which is straight integration of Hamiltonian density, and you should find out that this is same as energy, summing or mode. Plus some divergent bits. As we saw for scalar field derivatives. Okay, so I'm just saying everything works out as it should. No, I mean, depending on normalization, maybe just repeat that. Okay, so this is not the most exciting part of the story. So let me just state a lot of those facts. Then we want to talk about more exciting case of massless case. But are there any questions so far? So what we have talked about, we just have talked about the fact that for profile theory, by understanding that there's only 3 independent degrees of freedom, we figured out which variable we have to impose commutation relations. So that's basically the story.
We pass the Hamiltonian, we impose the equal time commutation relation, and then as you would expect, you can write down quantum field, and then you can figure out correct commutation relation for creation and annihilation operators. And in terms of this, you can also rederive Hamiltonian. And you see that this is obviously this kind of expression. So whenever you excite a mode with a momentum P and polarization R, you will have energy E. You're just summing up to get total energy. So it's all expected. Okay, good. So so I'm debating if I start writing down another boring long list of final rules, or I just pass on to massless case. So maybe we can actually pass on to the massless case, because now you start seeing more physics of it, and then we can come back and then we can talk about final rules. Let's actually test. Okay, now we have everything defined.
그 DIVGT는 답은
Yes, diversity. Yes. And then we know how to kill it by either imposing normal ordering and so on and so forth. We talked about this. Okay. So now let's talk about massless case. So we're gonna take now this goes to 0. And then Lagrangian is just this. Right? If we naively take the mass S goes to 0, assuming this limit is well defined. Okay. Now there will be subtlety here, and we're gonna talk about that subtlety. So one, just naively, we discovered that L is invariant under if you just make this transformation. And then we're going to spend some time to understand the meaning of that expression. So here, statement number 1 is that, okay, so this is my action now, okay, which we derive. And we observe for now that this Lagrangian is invariant under this particular transformation. And here, key is that this parameter is space-time dependent parameter. Okay, so what does this mean? Okay, understanding this sharply and deeply is the goal of the next 20 minutes or so, or 30 minutes. So this thing is called actually gauge transformation, and you probably know. And crucially, this is not a symmetry transformation. Instead, as you will see, this actually encodes that this is related to a redundancy of our description. So let's understand what do I mean by all of this. This word. Okay. So first of all, let's see how this is invariant under this. Okay, but that's quick to see because F mu nu, which is product of F mu nu is this. And obviously, if you do make this transformation, F mu nu transform. See, if I only keep the transform, transformed part, is that basically nu alpha minus nu alpha, which is 0. So it's not only that Lagrangian is invariant, but actually each of these pieces are, each of these two pieces are invariant under this transformation. Okay, so let's now understand the meaning of this statement. So, good. So let's recall for massive case first, because we're gonna have to take the limit to see the meaning of this thing. Recall for massive case, right? So for given momentum p mu, we had first of all, we had a set of polarization vectors. There R goes to 1, 2, 3. And then not only that, you remember that polarization vector has to satisfy this transversality condition. And in fact, it is because of this particular condition that these three basis vector should be momentum dependent. Okay? So what do I mean by that? A, we know that given this is time-like vector, this condition tells me that this should be space-like. So we should have three space-like vectors. Talk about this. So if you accidentally just pick a constant vector, suppose somebody has some p, you say, okay, I don't care about that. But so let me just pick a three space-like vector. Okay, so this is constant. You might say, oh, I have seen this because last time I introduced this particular basis. But that was for certain base, certain choice of momentum, which was brass frame. Okay, so in this frame, this is good choice. What I'm saying is that epsilon as a basis factor for three polarization degree of freedom is momentum dependent. So if you accidentally pick this basis, obviously, if you do make it a Lorentz boost, right, which mixes up one of the spatial component and temporal component. So if you just then perform a Lorentz boost, then you can turn on all of a sudden time-like component, which you didn't want to see. In other words, there's this mixing. So this part of the comment I'm making here is just to make sure to deliver that this polarization vector is a momentum dependent as is captured by this particular resolution. Okay, so you pick P, you figure out epsilon. So that's comment number one. Now, so then crucially, these three, they mix each other. Under the Lorentz transformation. I want to make that particular comment sharp. So let me do it. So what do I mean by this? Okay, so let me make that sharp. So what I mean by it really is this. So for any given time-like p mu, which I can write in general in some energy and momentum, right? And then here I'm again considering massive case. For any of such p, we can always go to rest frame by boost. So let me express that place as this particular equation, where mu is mass 0, 0, 2. And then this is my notation for Lorentz boost. Okay, so for massive particle, for any choice of for momenta, time-like for momenta, we can always go to the rest frame. Okay, good. Now, in this particular basis, then I can choose this set of bases. Okay, so if I go to the rest frame, I can choose these three bases. Epsilon 1, 2, 3. Now, since if I change P or momenta, I have to pick my basis again, right? This basis epsilons are momentum dependent. So therefore, the meaningful sort of Lorentz transformations I can ask is those that leaves, say, for instance, the K invariant. Let me say that again. So there are a set of Lorentz transformations such that it leaves K invariant. Okay, so I pick a particular momentum, in this case, a rest frame. Then there are a set of Lorentz transformations that leaves that momentum invariant. And this sort of transformation, or this sort of set of transformation, is called a little group. For K. Okay? What is the significance of little group here? Well, by definition, it does not change K. Therefore, by definition, the set of bases doesn't change. By which I mean, at best, what it can do is it can just rotate among themselves. It's not going to actually modify things, okay? But it can just rotate these three vectors into each other, okay? So we know that therefore, in this case, that by looking at this, you can ask, what is the little group for massive things? And here, by going into this rest frame, I have not lost any generality here, right? Because for any P, I can always go to them. So this applies to any massive particle trajectory. So in this case, you can see that little group is SO3 because you can pick any 3x3 matrix acting on these three blocks, and that does not change K. Okay, so you learn that the little group for massive particle is SO3 rotation. Or if you want to, go to slightly, universal cover, it is actually SU2 rotation. And under this SO3 rotation, you see here, because now if you look at this, this is a validated basis for that rest frame. This is literally three basis vectors, right? For three-dimensional space. So they will mix up each other. Okay, so therefore, epsilon1, epsilon2, epsilon3, I'm just gonna write it as this notation. They will just mix up each other. And this is great, because if they did not mix each other under little group transformations, what does that mean? I have not constructed, so if this was not the phenomenon, then I have not constructed actually, one vector representation. Instead, I just had, as we wrote it before, 1 plus 1 plus 1 representation, right? So it's good to see that actually happen, and hopefully it's totally clear that that's actually happening here. Okay, because literally you have a 3 also on the vectors, they will mix up with the rotation. Yeah, all I was trying to say was that this mixing shows indeed, as we already talked about, we constructed what we want. Okay. Yes.
한마디만 붙였는데, 그러니까 지금 믹스업 되는 경우 일일이 안 되지 않나요?
Yes. Because there's a mixing, it cannot be 1 plus 1 plus 1. Right? If it were 1 plus 1 plus 1, they should not mix each other. Right? They're separately irreducible representation. Okay? Irreducible representation means that they mix up each other.
이체 그룹이 항상 그 SO N 1,2 같은 데서만 보이거든요.
No, so little group notion itself is that for any point on the manifold, one set of transformation that leaves that point in there, in the sense of manifold.
한 포인트만 그럼 그 포인트에 디펜던트하게 그 그룹들이 정되는 거.
Yes,
인버스.
yes, if you want a mathematical. But once again, as I said earlier, this is true for every massive particle. We'll talk about massless very soon. Okay, so that's good. So that's what's happening as it's supposed to be. But this is what we were trying to understand. So let's keep moving on. Now, if I go to more general frame, on the other hand, so for instance, let's go to E, and then maybe EZ. We also talked about this example last time, right? So then, in this momentum choice, I can pick the first one to be 0, 1, 0, 0, and the second one to be 0, 0, 1, 0, and then the third one, we picked it to be PZ 0, 0, E, which is orthogonal to that. But since we wanted to have a normalization in such a way that epsilon R, epsilon S star, we wanted to normalize this, right, as a 3D factor. So that's why we divided by 1 over n last time. And then we talked about what would go wrong if we look at the very high energy process. Anyway, but for now, let's focus on this. And once again, it should be true that there's a little group, even though it's not very clear to see, but nevertheless, it has a little group SO3, and then under that, all 3 mixes up. Okay, good. So far for massive case. Now we are going to move on to massless case. But before that, any questions? Okay, so then let's actually move on to let me just say one obvious thing, but nevertheless it may be useful to see. So then since I picked a particular basis, any physical polarization, which may be linear combinations of basis vectors. So if I write it as this, which will be linear combination of basis vectors. This is completely the case. So if I, use notation, then if I call that to be just epsilon, and then this I just call it a basis vector, and then this is my coefficient vector. Okay, then obviously the norm of these things will be CR squared, C1 squared, C2 squared, C3 squared, if I obviously normalize my basis vector as this, so auto normalize, which I have done it, because if this minus sign was precisely to make sense that as a 3D vector, it has this normalization. Okay, so it's just the trivial statement for now. Okay. And in terms of amplitude, this has following things. So if I had a process where there's a fermion, scalar doesn't matter, then at least one vector or something like that, then for this vector line, there's associated polarization vector, right? Because if you look at it, this is like there's a vector particle, and then it's annihilated at this interaction vortex X. Okay, so annihilation A at epsilon mu, and then annihilation. So it is associated with epsilon mu. So the amplitude, if I write it as M or A, Fi, if you want, we'll have at least one factor of polarization for this particular vector line. And then, since I know that amplitude must be Lorentz scalar, this should multiply to some Lorentz vector, mu. So this is Lorentz for vector. Therefore, this also should be Lorentz for vector. And Lorentz invariance of this amplitude, obviously, is a statement that if epsilon, which is a function of p, goes to mu nu, epsilon nu, p, then this 4-vector amplitude also has to shift. Same way, such that the contraction is Lorentz invariant. Now, so far, everything seems you might find it too trivial and true. But let me make a one statement, which is actually important, as we will compare or contrast to the massless case. So what am I talking about here? What I'm talking about is the following. So we decided to use a vector field, right? So we decided to use a vector field to describe some physical degree of freedom. And for massive case, so for massive case, that means that I wanted to describe the 3 degrees of freedom, but using 4 component vector field. Okay, yes.
Due to the transversality condition.
Yes, there's that. But nevertheless, we pick this object. You might say, oh, was that a crash? It was not, as you said, there's a transversality condition. So, but the nice thing was that there is actually nice representation, which only can contain 3 degree of freedom under the Lorentz. So there is no actually mismatch, if you like. Okay? So using a vector field to describe 3 degree of freedom, given the fact that we know there's a 3-dimensional Lorentz representation, everything was packed in nicely. In fact, that was reflected by the fact that polarization vector actually transform linearly under Lorentz transformation here. How did you see that? Well, I described it here, right? So for any given P, you go to the rest frame, there's a linear group SO3, they just rotate each other as a linear rotation. So they did transform linearly under the Lorentz transformation. So everything was smooth and nice. So now we are about to go to the massless case, and then some of this will start breaking down. Okay, the question is, we're going to still use A mu because that's cool. And then we're going to we'll try to describe or see what happens if you want to use that nevertheless to describe a massless case. In this case, we will see that we will have only 2 degrees of freedom on the other hand. And what is the representation that only contains 2 degrees of freedom, but has polarization or plus polarization 1 instead of a half? Okay, so here we will see some mismatch. Yes,
왜 중에 분을 한번
I haven't, so I will. So you haven't missed. Good. Okay, so that's the subtlety, and this is deeply rooted into that. Okay, so that's what we want to see. Skip this much. So let's now see what happens. So let's take the limit. Let's take this limit. So in this limit, once again, if I pick this direction, first of all, now this goes to, if I take the massless limit, now this goes to E0, 0, E. Okay, so that becomes the same as that, as you know. Now, that's okay. Epsilon 1, 12 are just fine because they have this form and this form. So far, so good. Okay. So I'm naively taking the limit. And then let's continue. So what about epsilon 3, which I called it previously epsilon L to say it's a longitudinal mode. Now, if you ask yourself, okay, I want to find something that is perpendicular to this, right? Okay, so that looks like, again, it should be E, 0, 0, E, because that is perpendicular to that. So if you recall, previously I had PZ 0, 0, E. And then I put 1 over M so that this has a norm minus 1. Okay, so if you naively try to take that limit, okay, that's just sketchy. So here, instead what I say is that let's start out with this. And then by just taking this, I know it should be proportional to this. Okay, normalization, let's worry about later. Okay, so far so good? Okay, now, let's go back and ask about this question of living room. So now, if I, for any massless particle trajectory, I can always go to this frame. So the same one, which is parallel to the massive case, is that for any P, which had energy, which is the size of basically free momentum, and then some random free momentum. So this is guaranteed to be massless momentum. It's going to be 0. I can always bring it down to this frame. Okay? Just like I had let's boost. So if I call this to be now K, if you like, that's the connection. Okay? Now, what is the little group of this? Yes, the same question. Okay, the logic polarization vector is momentum dependent. So this is a momentum dependent function. Then what I'm saying is that for any massless case, I can always go to this like frame like boost. And then I want to ask Lorentz transformation now. So what is the little group? The least K variant for massless case. Turns out this is naively SO2 because there's a two component that is 0. You can just mix them each other without modifying K. It turns out that actually full little group is bigger. It's an ISO2. If you like, this is two-dimensional Euclidean group. So in addition to SO2, which is basically U1 phase rotation, there's also two translations. There's a two-dimensional rule. In addition to the rotation, you can actually have a translation. Okay, so it turns out full little group is ISO2. I think it's inhomogeneous.
Isn't that isometry?
Sorry,
I thought it was isometry.
isometry.
Yes, isometry in two-dimensional space because the translation is also isometry.
That's right.
Rotation also isometry.
Yes, yes. So it's literally two-dimensional Minkowski space, sorry, Euclidean space, and then you ask the maximal isometry, which is just like in 4 dimensions, there's a 3-dimensional rotation, 3-dimensional boost, there's 4 translations, right? So far we have forgotten that. But if you go to the 2 dimension, I'm saying there's 2 translations also. That's this. Okay. But then this one has a listed subgroup, which is SO2, which is also U1. And then this is generated by, so this thing is, in this particular case, is generated by I theta A3. Because here momentum is along the third direction, right? The rotation that makes up X and Y component is nothing but rotation with respect to Z direction. So this is not coincident. You might say, where the hell, J3 all of a sudden picked up? Obviously, that's picked up because I decided to go to the frame where momentum is along the Z direction. So this is nothing but helicity. Okay? So this is actually, if you wish, this is actually, momentum direction times J. Okay, so now we first can answer this question, 2 degree of freedom, at least at this level. Now, that means that if I want to have a physical state, which is an eigenstate of this thing, so basically I'm asking what is a helicity eigenstate, but as having a spin 1, because I'm talking about vector representation. Vector representation has either scalar or spin 1 representation, right? But I already projected out the spin 0, 0 representation. So I only work with the spin 1, 0 case. Now that means now if I actually take the massless limit, the question becomes, what is the helicity eigenstate of the spin 1 state? Obviously, now you can only have helicity, which is this eigenvalue, J3 eigenvalue is plus minus 1. Right? Because originally it is a +1, -1, 0. But then I'm asking only helicity I can say, so you can only plus or +1, -1. That's why it has only 2 degrees of freedom. This is true for any massless case, by the way. So massless case, not 1 here, but any massless representation only has a actually not any, I realized, except the scalar. So higher spin massless representation only has a plus minus h degree of freedom, 2 degree of freedom. Okay, so now almost there to be able to answer this question. So let's keep moving.
Professor,
Yes.
so are you trying to say that defining spin is not valid in this case?
Yeah, so in the mathless case, the only meaningful quantum number is not full spin, but only the helicity. So spin is meaningful if you deal with the massive case, because there, as we saw, little group was SU2 or SO3. So now it captures the entire spin. But if you project it onto massless case, then the only meaningful eigenvalue is helicity, which is, if you like, remnant of a spin or projected to the longer propagation direction. And it makes sense because if you had a massive case, then it can never be faster than light or equal to the light. So you can always boost so that it stops the particle. You look at the entire three-dimensional rotational structure. But if you had a massless particle, then it propagates at the speed of light. It can never catch up by any boost. So you can only access to the speed projected along the direction of the propagation. That's the entire information of the black hole. That's the concept.
J3에서 영웅을 왜 빠졌었지? KAIST 쪽에서 그 J3가 스핀 1이면 펠마 1하고 이제 제로가 있어야 되는데
Yeah.
제로를 지금 뺀 이유가
Because if you project the spin along the direction of propagation, but since we're talking about the spin 1 particle, you can check that maybe you can just square this to see this can never have a zero eigenvalue. So the exercise is you want to check that this thing cannot have so there's a best way of dealing with this question. This is a good question. The best way of dealing with this question is not what we've been constructing so far. Okay, so there's a representation of a Poincare group, and then you can define that in terms of two. Okay, let me just say a word. Two Casimir operators of the Poincare algebra, and there's a one called the mass square. The other called the one of the vector is called the Pauli-Lubansky vector. If you square that, is related to the spin. But in the massless case, you can actually project onto. So in that language of constructing Poincare representation, you can actually see that there's only two representations. Here, let me see if it is possible to show. So the question is how exactly we can see that J3 equal to 0 is projected out instead of one or the other. Yeah, so good. So one way to see that is because suppose I had a spin 1 particle, so this is separate. So suppose I had a spin 1, eigenstate of a spin 1 particle, so there's a momentum, and then suppose I'm dealing with a spin 1. Okay? So then if you make Lorentz transformation, in this case helicity transformation, J3. So then suppose I make a theta equals 2 pi rotation. Okay. So acting on and actually that rotation is helicity one state. That's the right thing to say. So then you're gonna pick up. Okay. Realize this doesn't break the degeneracy. And since for bosonic state, which I'm dealing with, is helicity 1 or integer value, since you have to go back to your cell, you find out that this should be quantized to be 2 pi times z. That. And okay, so okay. Actually, I realized that it does not close the loop. At least you can see that it should be integer helicity. Yeah, probably one has to look at the way I told you, meaning looking at the representation in terms of cabinet operators and the actual constructing representation space. Let's see. Let me think about whether that is captured in this language too. Then I think of that. Okay, any other question? I'm almost about to hit the function of today's lecture. Okay, so then let's do it. So if we take the massless case, massless limit, so this is observation. The point is that now, this is, in a sense, one of the most important part. The point is that now, unlike in the case of massive case, where three vectors just rotate happily nicely, forming complete representation. Massless case, if you now do make a linear transformation, although this SU2 subgroup only mixes up these to each other, because that's the rotation with respect to the z direction, it mixes x, y component. But there are other elements of a full linear group, which is ISO2, that actually mixes up all three together. Okay? So the statement, therefore, is that, let me actually use that part of space. So that then what happens in the massless case, which is very different from massive case, is that under Lorentz transformation, for instance, epsilon 1 mu goes to, which is obviously momentum dependent, but I'm going to suppress p for now. Like C11 under Lorentz, epsilon 1, C12, epsilon 2, and then they're going to mix up the third, the longitudinal momentum part, which 1, 3, that looks like along the momentum direction, up to numerical vector. And then similarly for the second polarization vector, under the same Lorentz transformation, that you will mix out. Wow. And this is not surprising if you reach, or it is surprising, I don't know. Because as I told you, unlike in the case of massive case where you had a complete representation, which was a D 1,0, massless case, there's no such closed representation that only mixes up two vectors only. Okay? So the only option is that they actually mix up together. And this is exactly what's happening here. So this is one of the, so the statement here is that for massless case, you can always go to the line-like frame. There's a linear group, which is ISO2. And then under the linear group, it's not like only these two mix up, but I'm saying all three mixes up, which is, if you like, continuation of what happened for the massive case. Right? For massive case, if you pick this as actually one of the possible physical degree freedom, you saw that they're mixing all together. So in general, therefore, what happens is that for general polarization vector, under the Lorentz transformation in the massless case, is not just transforming nicely under mu and u epsilon 2, but actually it picks up p mu dependent this, which is now some transformation parameter alpha, which is parameterizing this. Okay. And what does this mean? Now, so this is a fact. Now the question is understanding meaning of this equation. What does that mean? Why are we having this phenomenon? And I told you the answer already. So I wanted to describe a 2-degree freedom. So that was what I wanted to have. But then I picked a mu to do that, which is the 4-degree freedom with it. You can say, oh, why are we doing this? And the reason why we picked to pick a mu to describe a 2-degree freedom was to have, if you like, manifest Lorentz invariance. Here I put manifest. What do I mean by this? So if you use one of the well-defined tensor spinor representation of a Lorentz group, that it is very easy to make sure Lorentz invariance of action. So for instance, I know if I write down this, this is Lorentz invariant because there's a contractive, right? And if you solve this, for instance, modulo sum that we understood by now, you say, yeah, this is Lorentz invariant because Lorentz tensor, right? So there's a certain benefit of using well-defined tensorial representation of Lorentz group because now it's so easy to make sure things are Lorentz invariant when you try to write down the action. But precisely because of that, because you demanded manifest Lorentz invariance and locality, I'm writing everything at each point of space, then there's this mismatch. There's this crack. And that crack was exactly captured by this equation. So under the Lorentz transformation, those two does not just nicely mix each other, but actually picking out some weird factor. So it goes out of that representation space if you want. Okay? So the resolution to this phenomena is that you have to demand that this is actually a physically, so let me just write this way. Epsilon and that, you have to say that they are identical physical state. Okay? So morally, what you wanted to say, I have two. I know there's a lot of garbages, but two. And then I do make a Lorentz transformation. What I wanted to say was that they just mix each other. I know there's a lot of garbages, but how to deal with that? I have to say that, I know I see this problem, but I have to say that I have to demand that mathematically this is equivalent to that configuration. So this is a identification relation. So this, you're okay, right? This is nice Lorentz transformation. This, you're not okay, right? Because this is like something you don't want to see. So therefore, more precisely, let me just make it precisely. So when you see this, what you want to say, therefore, is that whenever you see epsilon, and then epsilon, not this, but off by only this p mu dependent piece, I want to say that they're just physically identical. There's nothing different between these two. I'm just saying they're same thing. Okay, you have to say that. Then this is equivalent to that, which is a happy expression. This is nice linear Lorentz transformation. Yes.
지금 로렌츠 트랜스폼이 아닌 어떤 다른 종류의 트랜스폼을 그러니까 어떤 논리니한 트랜스폼의 생각을 지금 더 하고 싶으시다는 거죠.
No, what I'm saying is that I first did honest Lorentz transformation. Okay? I just try to derive Lorentz transformation. If you do that, the matchless case, the polarization vector actually not only transformed as if it is a nice homogeneous transformation, linear transformation, but it also picks out a inhomogeneous piece. And then I want to make sense of that. And the way I make sense of that is based on physicality. Physicality means that I know I always wanted to describe only 2-degree freedom. Whenever I see some other weird behavior, I have to accept or swallow that this is because of non-minimal description I decide to do. There was a redundancy in the description. It has a more than 2-degree freedom I wanted to describe. Because of there was a redundancy, I had challenges here. And the way I deal with the challenge is that I don't view this as actually a separate transformation. I have to say that this is the same identified configuration as this original one. Then everything transformed as if it is a nice linear homogeneous transformation. So this is an identification rule. This physically identify with this. So therefore, feel the space of this theory. Now, if you actually go back and remember, what was A? A was epsilon mu e to the minus I p times, right? So that was a plane wave solution. But everything I discussed in terms of polarization vector. So if you Fourier transform back to the position space, that identification rule is exactly this. Okay. Now, therefore, what I learned is that action is invariant under this. This is not a symmetric transformation. Symmetric transformation connects one physical configuration to another physical configuration. So here's the one state. If I do make a rotation, that's another state, which is well-defined, nice physical state. But symmetry tell you there's a good relationship between two or many different physical states. The identification rule I talked about here is not a symmetry transformation. This and that are the same state, not different state, related by symmetry transformation. Okay, so it is a gauge called a gauge transformation, and then it is due to the redundancy of the description, as we talked about. Okay, since I decided to use this, which has more than I needed, but it basically makes it Lorentz invariance manifest and nice. So we understood that that this theory has this gauge invariance, but not a symmetry invariance. And then we are going to explore the meaning of that further. Okay, any other question at this point? Okay, I'm just gonna say one more thing and then I'll end. So next time we're gonna discuss how to couple this theory consistently to other matter field using Noether's method. For now, let me restate this in terms of amplitude. Okay, so once again, you understand now that a mu is identified with this, or in terms of polarization, these are to be identified. So the field configuration, in other words, if you ask, okay, I have a lot of different possible field configurations, but then they are packaged in terms of this equivalence class. Okay, each configuration is not a single configuration, but each physically distinct configuration is the equivalence class that is controlled by this equivalence relation. Okay. So now, again, let's consider amplitude. So there's a fermion, scalar, a lot of them, especially there's a one vector. And that is associated with epsilon mu. So once again, physical amplitude will have epsilon mu and some m mu. So I'm just considering here one photon case, one massless photon case. Now, since this is identified with epsilon mu plus t mu alpha, remember this is literally the same. Okay, so this is identification rule. And then that is fulfilled only if this vector valued amplitude already satisfies this property. So any amplitude that has massless vector boson in this case, okay, are consistent only if it satisfies this relation. And this is called, there's a name, word identity. And I guess we have a chance to talk about more full-fledged version of word identity eventually, but this is, if you wish, first encounter a baby version of that. And hopefully now you can read this in many different ways. But A, you can say this is because of the gauge redundancy, right? B, you can also say that that's because we wanted to have a manifestly Lorentz invariant and local unitary description of massless spin one particle. Okay, so if somebody say that word, okay, here's the expression, and this basically captures, okay, result or consequence of having manifestly Lorentz invariant local unitary description of massless spin one particle. Okay, hopefully now you can connect all those things to this equation. Okay, so I'll end here, and then I'll take questions.